because we're looking at P2's point of view. So P2 looks at things like the receipt. So you're still looking at second column, right? This is 0, this is a 1, and that's understandable because that difference is for P1. P1 ascending. But the others should be the same or even greater if they're there, but in this case it's the same. So 0, 0, so which means P1, P2 knows everything that P1 knows before sending this message, right? So it can now do a component-wise maximum and so it can change this to 0, 1, 0, so that this is clockwise, 0, 1, 0, 0, 0, 0, 0, right? So now, what about this? Now compare the second column with the second column here, right? So this last one, this is a 0, that's because of P3 sending it, but the other says 1, 0, this is 1, 0. So now you can just do what? Accept it and do a component-wise max. Remember, you are not incrementing while receiving here because that explicitly is stored in the column. So increment while you are sending. So just take a component-wise maximum 0, 1, 1, 0, 1, 0, so it is 0, 1, 1, and it is 0, 1, 0, 0, 0, 0, 0, 0, 1, 0. Okay? It's more straightforward. Let's do one more example. Okay, so we start with all zeros for the matrix. So here, this is a broadcasting. So P is example of unicasting. We are broadcasting. Broadcasting means you're sending to every process. So I'm sending from P3 to both P2 and P1. So what should I do? How to increment my matrix? You have here to start with all zeros, right? So how do I increment the matrix? You're sending this from where? P3. So which third row? P3's row, right? You increment while sending and you increment the row increase. Receiving is for column, right? And sending row. Okay? So go to P3's row, and to whom you are sending here now? P1 and P2. So which means you have to change this to a 1, which is this, and change this to the 1, which is this. Okay? So you have to increment those two to a 1 because you're sending from P3, that's what it means. This is the third row is for P3, you're sending from P3 to P1 and P2. Okay? So you send this as your timestamp in both the messages. Now looking at P2 first, this local clock value is what? Our matrix is all zeros, right? So how does it check now to receive or not? So check the second column. And this is coming from P3, so this one is fine, and the rest of the row 0, 0, same thing. So P2 can accept it, take a component-wise maximum, and have the same thing as its clock. I did not show it here, but it's the same thing. 0, 0, 0, 1, 1, 0. Good, yeah. So now P2 sends another message, it's a broadcast again, to P1 and P3. So how should P2 change this matrix? Go to the second row and you're sending to whom? P1 and P3. So increment this like this, and that's what is this. Okay? And include that in the timestamp matrix timestamp in both the messages. So this is the matrix timestamp that you're carrying. Same thing I'm repeating. Right? So this message goes here. Now we have to decide whether to accept the message as P1. The local matrix is this. Nothing has happened until then, right? So how do you check? Checks first column in the first thing, and the first column in the message is this. So it's coming from P2. So the difference could be 1 for should be 1 for this row, this something sent from P3 to P1 which P1 has not got, because if P1 has got, this would have been a 1, right? So that's not a 1, it is still a 0. And this message was sent after P2 received that message from P3, right? This message. So which means you have to wait at P1 until that message comes to P1. So this message now comes to P1 with this timestamp, and it's understandable that at P1 it is, because of this, it's a 1, right? So P1 can accept that, and it's also sent to P2, so that's why you have a 1 here, so the component-wise maximum. So now you compare this entry, matrix clock, with this, and with this. So you see here this difference of 1 is at P2, so that's fine, 0 and 1, but this is 1 here, and 0 here, and 0 here. So except that P2's entry, everything else is fine, right? So now P1 can accept it and do the component-wise maximum and change its clock. Okay, so that is its matrix-based thing. So if you look at the complexity of this, what is the complexity of this approach? You're looking at matrices. So storage-wise, you should not be efficient, right? So you have to maintain an n by n matrix, and now you again look at whether to include theta or big O. You have to always have n rows and n columns, right? No matter what you do. So which means you have to always have n square elements in your matrix, right? So that's why it's theta of n square. So it's not big O of n square, it is theta of n square. And similarly the messages, every message you send at least this timestamp, right? So every time you send, you put the timestamp, the matrix. So again, you have to have the matrix, the message, the timestamp. So that's again theta of n square. And in terms of sending, you can send as unicast, broadcast, depending on what you want. So if you do a unicast, you're sending to only one process. You're sending a broadcast, you're sending to all the n-1 processes. So that's theta of n, always n-1 for broadcast. Okay? Is that clear? So that's how you compare the three algorithms. And this I explained already. You increment the clock only while sending in the first one, which is the BSS algorithm, and the third one, the matrix one, because both are kind of broadcast based. In the sense, the first one is explicitly broadcast, you're sending to everyone, so you just increment while sending, because the others get to know due to that. Matrix we just saw that while sending, you're incrementing the entries for all the processes who are receiving this message. So that we are capturing that they should have received that message, right? So you don't need to explicitly increment while receiving. And this we saw that just previous to that, SES. We have to explicitly increment while receiving, otherwise the other processes don't know that you are receiving it. So that's why you have to increment this. Okay? Now let me just go through a small example for the next one. We'll do it next time, but just to give an idea. So the next topic is to collect what is called global state. The global state is nothing but a collection of the local states of all the processes and the messages on the channels. Channels means like when I have something like this is three processes here, right? So you have P1, P2 and P3, and let's say they can communicate like this. So what is the local state means? Every message that has been sent from P1 or received at P1 and some internal events that happened at P1. Likewise, the local state at P2 is everything sent from P2, everything received at P2 and all the internal events. So then we have channels like this from 1 to 2. It could be, you can think as unidirectional, like this. Okay? So all the messages that are in transit that have been still on the channel. So why I say transit? And first of all, what I mean by global states, a snapshot of the system at some point of time. You know, this is all time axis, as I showed you. I want to collect the state of this whole global, all the processes at some instant of time. Okay? So of course you know we cannot synchronize the clocks tightly across all the processes. So there could be like I collect a timestamp here, and I collect a timestamp here at this process, the snapshot, and this snapshot here. And we'll see later an algorithm for that. So if this is the kind of what's called a cut. Cut means I'm cutting at some time instant at all these processes like this. I need to use that information to figure out whether this is a consistent cut or an inconsistent cut. If it's a consistent cut, we could classify also as strongly consistent. Okay, so we have three things: consistent, strongly consistent or just consistent, and inconsistent. So let's see what does it mean, and then we'll go through it next time in the algorithm. A consistent cut is something where if the sending of a message is recorded, the receiving of the message may or may not be recorded across all the processes. For example, if you look at this, right, this includes this message as well as this message, right? Because in time, starting from here, we forgot about this cut. If you collect the cut here, the blue line, it includes this message as well as this message. This message, the sending is recorded here because this is recorded prior to this. You record at this time and it's recorded here. The sending event is recorded here. The receiving event is recorded here. You collect the snapshot here. So the snapshot includes that this has been received. Because here, this has been sent and recorded at this process, whereas this one is you collect a snapshot prior to receiving, right? So which means if you collect a snapshot here for all this thing, nothing has happened, but that's fine. For this message, the sending event has been recorded, but the receiving event has not been yet recorded. So you can say that message is still in transit, right, on the channel from P2 to P3. Okay? Whereas this has been sent as well as received. So there's nothing on the channel from P1 to P2. Okay? As far as this cut is concerned, there's nothing on the channel from P1 to P2. It was sent and it was received. Alright? So at least one message is in transit in a cut, but everything is consistent. So again, when you say it's consistent, look at this case. The snapshot was collected here, the sending event was recorded after collecting the snapshot. Right? So which means no other process should have recorded this as received because the sender state says it has not been sent because the sender state is this instant. Right? The sender state does not capture the sending of this message. Whereas you see here, the receiver state was captured after receiving of this message. So the receiver says I have received some message, whereas the sender says I have not sent it. So that's like an orphan message that is shown as received, but the sending event is not recorded yet. So we call that as an inconsistent cut. Doesn't make sense, right? That's what's called inconsistent. Whereas here it makes sense because the sending is recorded, so the message is just in transit. Okay? Now when we call a consistent cut to be strongly consistent, when there's no message in transit, as you see here, for this green line, the local states are collected at these time instance. So the sending event is recorded as well as the receiving event is recorded, and no other message. So there's nothing like this that crosses the cut. So you can also look at it like this. If the message crosses the cut, it means there is something in transit. Here, there's nothing crosses the cut. There's nothing that goes like this. So if it crosses the cut, that means it's in transit. Sent here, not yet received, because you're selling the snapshot here. But here, there's nothing that crosses the cut, which means everything sent is also received. So we can call that as consistent but also strongly consistent cut, because there's no message in transit. Okay? So next time we look at more on this and an algorithm to record this cut, global cut. Okay? And then we'll proceed.